In this video, we're going to compute curvature. In the first example, we'll compute curvature for a line, and we'll show that it's 0. In the second example, we'll compute the curvature of a circle. And a circle has curvature 1 over the radius. So we'll get 1/3 for our answer here. And then the third example, we'll compute the curvature of a spiral helix. So that's not going to be a constant. All right, the formula that we're going to use to compute curvature for these examples involves the arc length parameter, S. So the definition of curvature, if our curve is expressed in terms of an arc length parameter, is curvature equals, that's kappa, the Greek letter kappa, which looks like a K. Curvature equals the magnitude of dt ds, the rate of change of the unit tangent vector t with respect to arc length parameter s. And t is a vector. It's the unit tangent vector. So in general, if you have a curve r of t, then t of t, the unit tangent vector, is r prime of t divided by the magnitude of r prime of t. But if we use an arc length parameter, then our curve is given by r of s, and the unit tangent vector t of s is equal to r prime of s divided by the magnitude of r prime of s. And the point is that the magnitude of r prime of s is 1. That's what an arc length parameter does for us. It makes the speed of the curve 1. So the magnitude of r prime, which is the speed of the curve, that's 1. So t of s is just r prime of s. So we want the magnitude of dt ds. All right, let's see example 1. Let ABC be a unit vector, and then show that this line has 0 curvature. The line goes through the point x0, y0, z0, and it's in the direction of ABC. So we have x0 plus as, y0 plus bs, and c0 plus cs for the components of r. Now we wrote s here as if it was an arc length parameter, and the reason that it is because ABC is a unit vector. If we calculate r prime of s, it is simply ABC. Because this is a linear function, the derivative with respect to s is just a. Here it's b, and here it's c. And the magnitude of r prime of s is 1, that's given. So that means that our curve does have speed 1. Our parameter s is an arc length parameter. Let's abbreviate that. And therefore we can compute k very directly. K is the magnitude of dt ds, which is the magnitude of, well, t is the vector ABC, because t of s is r prime of s. So r prime of s here is this vector. So we want the derivative with respect to s of the vector ABC. That's t. And that's a constant vector. So the derivative is 0. The 0 vector, it's 0, 0, 0. And the magnitude of the 0 vector is the scalar 0. And so the curvature of a line is 0. which is something that we would expect from a mathematical object that measures curvature. A line does not curve, so 0 curvature for a line. Second, a circle of radius 3. We don't even have a parameterization given to us here, so to parameterize a circle, let's say in a plane, and we may as well just make the center the origin, because the curvature shouldn't depend on where the circle is located. So a circle, center at the origin, the parameterization is going to be r of t equals, and we're going to have the radius times cosine of t, and then the radius times sine of t. And if you wanted to put it in 3 dimensions, you could put a 0 there, or you could just lop off the 3rd dimension altogether. It's not going to play a role because of that 0. And our radius, we're told, is 3. So let's amend this to have 3's, where t is between 0 and 2 pi. But this is not an arc length parameter. R prime of t is negative 3 sine t, comma 3 cosine t. And the magnitude of that is 3, not 1. So this is a curve with speed 3 and not speed 1. So we have to turn it into a curve with speed 1 by reparameterizing it. And if we just take s equals t over 3, that should do the trick. So let's make r of s equal to 3 cosine. Actually, what I want is, I think here, s over 3. Then if I take the derivative, the 3's will cancel, and I'll just get cosine s, and then I'll get a sine s and a cosine s, and that will have length 1. So 3 cosine s over 3. So really, it's t equals s over 3, or s equals 3t. And this one will be 3 sine s over 3. So that should be an arc length parameter. We can just double check that. R prime of s is 3 times negative sine of s over 3 times 1/3. And the 3 and the 1/3 cancel. And here we're going to get cosine s over 3, because the 3 and the 1/3 are going to cancel. And the magnitude of r prime of s is just the magnitude of a sine and a cosine, and that's going to be 1, because sine squared plus cosine squared equals 1. So this is indeed an arc length parameter. Okay, that means then that we can calculate the curvature from this parameterization. So the curvature is the magnitude of dt ds. T is r prime, since we have an arc length parameter, so this is the magnitude of the derivative with respect to s of the vector the derivative with respect to x of the vector that we have here, negative sine s over 3, comma cosine s over 3. And the magnitude of this is going to be 1/3, because of the 1/3 that come out in the derivative. We're going to get a cosine and a sine, and we're going to get a times 1/3. So this is the magnitude of the derivative here is negative 1/3 cosine s over 3, and the derivative here is negative 1/3 sine s over 3. And the magnitude of this, since cosine squared plus sine squared is 1, we're going to have 1/3. We can factor out a 1/3 here, and we get 1/3. So there's our curvature for a circle. The curvature of a circle is the reciprocal of the radius. So a small circle has a greater curvature than a bigger circle. So this one has a smaller curvature, and this one has a larger curvature. Does that make sense? If you're driving your car around a circle, which one is going to feel like it's curving more, a small circle or a large circle? If you're driving in a very large circle, you might not even notice that you're not going straight. If you're driving in a very small circle, then you'll have to kind of turn the wheel very hard. So it makes sense that there's more curvature, a larger K, kappa, for a smaller circle. So the curvature of the circle of radius r is 1 over the radius. Large radius, small curvature, small radius, large curvature. Okay, now let's have a look at the last one. The third one, we had a spiral helix, 2 cosine, 2 sine, and then 5t. We had 2 cosine 3t, 2 sine 3t, and then 5t. This is almost certainly not an arc length parameter, so we will have to create the arc length parameter, and we do that from there's a formula for that. S is the integral from 0 to t of the magnitude of r prime of t dt. Sorry, I need to use a dummy variable here, so I should call that one something else. Anything else, t is in use, so let's just call it u. Magnitude of r prime of u du. And this will be an arc length parameter, because if t is, say, 1, then s will be the length of the curve over the interval 0 to 1, and so s will match with the arc length. Okay, let's put the details in here. Let's calculate this integral. We need the magnitude of r prime. So r prime is negative 6 sine 3t, 6 cosine 3t, and 5. And that's a vector and a magnitude and du. So that's the integral from 0 to t of the square root of 36 sine squared 3t plus 36 cosine squared 3t plus 25 du, and this is a constant. 36 sine squared plus 36 cosine squared is just 36, and 36 and 25 are 61. So this is the integral of the square root of 61. So this is the square root of 61 times t. So s is the square root of 61 times t. So this curve did have constant speed of square root of 61. To make it have speed 1, we will let t equal s over square root of 61, because s equals that. So just solve for t. T is this. So it's like the circle example. We didn't do this calculation for the circle, but we could have, and we would have gotten the same relationship here that we have still on the board between t and s. So now we'll just change the parameter to the arc length parameter. So we'll change r to r of s is 2 cosine 3t. 3t is 3s over the square root of 61. And then 2 sine 3t, so that's 3s over the square root of 61. And then 5t is 5s over the square root of 61. So there's our new parameterization, and now s is an arc length parameter. So we'll calculate t of s, that's not an s. We'll calculate t of s, which is just r prime of s, the unit tangent vector. So that's going to be, we have to take a derivative of cosine, that's a negative, and we're going to get 6 over the square root of 61, and then a sine of 3s over the square root of 61. And then here we need a derivative of sine, that's cosine. There should be a comma. That's a cosine, and then we have this constant coming out from the chain rule, so that's going to give us the 6 over the square root of 61 cosine of the same angle, 3s over the square root of 61. And in the last component, we just have 5 over the square root of 61. So this is t of s. Now we need the derivative of this with respect to the derivative of this with respect to s. So we need dt ds, which is going to give us a negative 18 over 61 cosine 3s over the square root of 61, and then an 18 over 61 sine with a negative of 3s over the square root of 61, and then a 0. So that's dt ds, and we need the magnitude of that is kappa, our curvature. So we just need the magnitude of this vector. And this vector has a magnitude of 18 over 61. We can factor out the 18 over 61, and then we have just a cosine and a sine, which has magnitude 1. So our curvature is 18, it is constant. It does have constant curvature. This spiral helix, we're going around in a circle as we go up in the z. This is the z direction here. The spiral helix, we're going around in a circle. If we look at it from the top down, it would just look like we were going around and around in a circle. But we're also going up, rising, because of the third component of our vector was 5t. We had circular components here with a cosine and a sine, and then we had a z component of 5t, so as we're rising, as time goes on, the z increases. But we did have constant curvature. It was 18 over 61.